So there's something called the fundamental theorem of algebra. It's kind of important because it's fundamental, and algebra is a big topic. So it says that every polynomial equation with degrees greater than 0 has at least one root in the set of complex numbers. Complex means real and imaginary. So a polynomial function with greater than 0 degree, so that can be a first, second, third degree polynomial, has at least one root in a set of complex numbers. All right, let me show you what this kind of means. Let's talk about this one right here. Here's the graph for it. This function has this graph. Do you notice there is only one root for this function visually? Which that's what it says. But what's the degree of this? Well, you should notice it's a fourth degree. How do we know it's a fourth degree? Well, if you take this power and add them, you get a fourth degree power. Because if you were to, basically if you multiply this and multiply all this together, your highest power would be a fourth degree, fourth power, when you multiply it all out. And it's a fourth degree, but it only has one root, and that's what this is saying. You should always have at least one root, at least one complex root. Now, there could be more roots in here you don't see. There's only one real root. There are more than that, and that's what we're going to talk about. There's imaginaries hiding that you don't see. So let's take a look. How do you find real and imaginary roots? For real roots, what you do is, for instance, let's take this one. What makes that 0? And if you solve that, you get x equals 2. So that right there is a real root. And look at the picture. Isn't that the real root right there? Yeah, there it is. Boom. X equals 2. All right? So what happens when I try to make this equal to 0? You can't. There's nothing you can plug into this to make it equal to 0 in the real numbers. In imaginaries, you can't. So this is like you're stuck. Oh, there's no root. There is. It's this imaginary roots. So again, our only real is 2, and that's why it hits right there. So how do we find the imaginary numbers that make this equal to 0? Well, what we do is this. We go x squared plus 9 equaling 0. All right, we minus 9 over. We got x squared equaling negative 9. We square root both sides. And when we do that, we get x equals, well, if you think about this, isn't this the square root of negative 1 times the square root of 9? So the square root of negative 1, isn't that I? And isn't this one 3? So the answer is 3i, but it's a plus or minus. If you remember when you square root both sides, you have a plus or minus. So your answer is plus or minus 3i. So what that means is, you actually have 1, 2, 3 complex roots. Because you have 2 imaginary roots and 1 real root. But the only ones that show up on your graph are the real roots. You don't see the complex roots. They don't show their face. But they do weird things to the graph sometimes, and you might like, why does it have that weird look? It's probably because there's an imaginary root hiding inside. So, according to the statement, this is a polynomial greater than 0, and it has at least one root in the complex numbers. Okay, this one actually has 3. 1 real, 2 imaginaries. So let's talk about the corollary to the fundamental theorem of algebra. A polynomial equation of degree n has exactly n roots in the set of complex numbers, including repeated roots. Oh, so this is slightly different than the last one. A corollary kind of means an extension or something that you build from it. And this is actually the more commonly stated fundamental theorem of algebra. That if you have 5 roots, if it's a 5th degree, that means I have 5 roots in the complex numbers, including repeated roots, meaning multiplicities. So whatever the degree is, that's how many roots you have in the complex numbers. It's just you could have multiplicities, and you can have imaginaries, and all sorts of fun stuff. So let's look at this one. This equation is this graph. Look at this. I have 3 real roots. So inside of this, I'm going to find 3 real roots. But according to this, shouldn't I have either multiplicities or 2 more roots to make 5? Because, oh, by the way, I didn't tell you it's 5th degree. Isn't that 1, 2, 3, 4, 5? If we go 1 plus 2 plus 2, isn't that a fifth degree? So for a fifth degree, but this only has 3, shouldn't there be 2 complex roots hiding in this, or a multiplicity? Now if we look at it, let's see what we get. Let's see what we come up with. All right, our real roots are -2, 0, and 2. Those are our real roots. So if we look at this, isn't 0 a root right there? So we know right away from that one, we know, okay, x equals 0. That's from that right there. Now, which one of these will come up with a real root? Well, if we solve it, isn't this possible? Where this one, can you tell that's imaginary? It never works. You can never do that. That's what you got to start watching for. You got to start watching for which ones have an answer, which one have those imaginary look. So what you're going to notice is this right here actually has an answer. If we write for this one, if we say x squared minus 4, it's an ugly 4, equals 0, and we add the 4 over, and we get x squared equals 4, and then we square root both sides, we get x equals positive -2. So those are my 2 sets of real roots. I have these 2 and this one for 3, and aren't those the actual roots here? It's kind of neat. This is why the squared happens as 2. You can see it visually. Sometimes people forget the plus or minus when they square root. Visually, you can see it. Now, the question again was, where are those imaginary roots or multiplicities? Well, I know there's no power up here, so it's not a multiplicity. So this must be 2 complex roots hiding, or imaginary roots, sorry. Imaginary, complex means imaginary and real together. So I messed that up sometimes, so sorry if I do. I'm going to set this equal to 0 and solve it, and this will give me my imaginary roots. So I have x squared plus 1 equal to 0. I'm going to solve this. So I'm minus 1 from both sides. I get x squared equals -1. I'm going to square root both sides, and I get x equals plus or minus I, or 1i. Okay, because square root of 1 is 1. So it's basically I. So right here, do I now have 1, 2, 3, 4, 5 roots? Some complex, some imaginary, sorry, all complex, because some are real, some are imaginary, and the corollary holds. If I have a fifth degree, I have 5 roots. Sometimes I have multiplicities or repeated roots. This one did not have a repeated root.